Welcome to the deep dive. Today we're tackling a topic that pops up, well, everywhere really, machine learning fundamentals.
Definitely a big one.
Yeah, and you've shared some great materials, Bishop's more theoretical stuff, Mitchell's practical perspectives. We want to kind of demystify it, right? Give people those aha
Mhm.
moments without drowning in jargon.
Exactly. Cut through the complexity, give a clear, structured view.
So our mission today, lay down a solid foundation using this material. Let's jump right in. Where do we start? Maybe the different ways machines learn.
Good place to start. Yeah.
Hmm.
Broadly, you can think of three main styles, three categories. It's really fundamental to get these distinctions.
Okay.
You've got supervised learning, unsupervised learning, and reinforcement learning.
Right. Let's take supervised first. What's the kind of core idea there?
Okay, supervised learning is, think of it like learning with a teacher or maybe flashcards.
Yeah.
You have inputs and you have the correct outputs to
Except,
the labels.
so you know the right answer already for the training stuff.
Precisely. The machine learns to map the inputs to the outputs based on this labeled data. Bishop uses that polynomial curve fitting example, remember?
Ah, yeah, trying to predict t given x.
Exactly. You get pairs of x, and the model learns that relationship. The whole point is for it to generalize, to predict t for new x values it hasn't seen.
So it's not just connecting the dots you gave it, it's learning the underlying trend.
That's the goal. And Bishop adds another layer, the probabilistic view. Instead of one perfect curve, you can think about the probability of different curves.
Okay.
You can even model uncertainty, like using a Gaussian distribution. So you don't just get an answer, you get a sense of how confident the model is. It's pretty powerful.
Yeah, that is useful. Okay, so that's supervised learning with labels. What about unsupervised? No labels there, right?
Right, no labels. Unsupervised learning is more like discovery,
Yeah.
finding hidden patterns or structure in the data itself without being told what to look for.
Like finding patterns yourself?
Exactly. K-means clustering is the classic example Bishop uses. You throw a bunch of data points at it, and the algorithm tries to group similar ones together into clusters.
Without knowing the groups beforehand.
Correct. It iteratively figures out the cluster centers and assigns points.
Yeah.
Back and forth, assign, update, until it settles. It discovers the groups.
So it's kind of like sorting things automatically.
Yeah, pretty much. And clustering isn't the only thing. Dimensionality reduction is another big one.
Right, reducing the number of variables.
Like principal component analysis, PCA. You take complex data with lots of features and try to boil it down to the most important dimensions, keeping the essential information, like summarizing a long report.
Okay, got it. Supervised needs labels. Unsupervised finds patterns in unlabeled data. What about the third one? Reinforcement learning. That sounds different again.
It is quite different. Reinforcement learning is about learning through interaction. You have an agent acting in an environment.
Like a robot exploring a room.
Could be. Or an algorithm playing a game. Mitchell's book shows that agent-environment loop clearly. The agent takes an action.
Okay.
The environment changes state and gives back a reward. Or maybe a penalty.
Like getting points in a game or losing points.
Exactly. And the agent's goal is to learn a strategy, a policy, to maximize the total rewards it gets over time. It's learning by trial and error, essentially.
Yeah.
Learning from consequences.
So it's not told this action is right, this is wrong, but more like that action got you a reward, that one didn't.
Precisely. It learns what actions lead to good outcomes in the long run. Finding that balance between trying new things, exploration, and sticking with what works, exploitation, is key there.
Fascinating. Okay, that's a great overview of the three main types. Now, say we've picked an approach. How do we actually, train a model and make sure it's actually any good? I hear a lot about splitting data.
Absolutely crucial. You can't just throw all your data at the model and hope for the best. You need to be smart about how you use it. That usually means splitting it into three distinct sets.
3 sets. Okay.
Training, validation, and testing.
Right. What's the training set for? Seems obvious, but
Well, yeah, it's pretty much what it sounds like. That's the bulk of your data, usually.
yeah.
And it's what the algorithm actually learns from. It sees the patterns, adjusts its parameters based on this data. It's the textbook the student studies from.
Okay. Makes sense. Then the validation set. What's its role?
The validation set is super important for tuning the model and avoiding a big problem called overfitting. We'll get more into that, but basically, models often have these settings called hyperparameters.
Like knobs you can tweak?
Sort of, yeah. They control how the model learns, but they aren't learned from the training data directly. You use the validation set to try different hyperparameter settings and see which ones perform best on data the model didn't train on.
Okay. Like a practice test.
Exactly like a practice test. Nietzsche
Yeah.
talks about pruning decision trees. using a validation set.
Yeah.
You use it to decide how complex the tree should be to generalize well. It helps you fine-tune.
Gotcha. So train on training, tune on validation. What's the last one? The testing set.
The testing set is the final exam. You keep this completely separate. You don't touch it during training. You don't touch it during tuning.
Keep it pristine.
Right. Only after you've finalized your model, chosen your hyperparameters using the validation set, then you run it on the testing set. This gives you an unbiased estimate of how well your model will likely perform on brand new, unseen, real-world data. Mitchell really stresses evaluating that true error on data that wasn't part of the learning process at all.
That makes total sense. Avoids fooling yourself about how good the model is.
Yep.
Okay, you mentioned overfitting a couple of times. Let's dig into that. What is it exactly?
Overfitting. It's probably one of those common headaches in machine learning. It
Mhm.
happens when your model learns the training data too well,
Too well. How can that be bad?
because it starts learning not just the underlying patterns, but also the noise, the random fluctuations specific to that particular training set. It basically memorizes the training examples.
Ah, okay, so it's like that student who just memorizes answers for one test but doesn't actually understand the subject?
Perfect analogy. It performs brilliantly on the data it was trained on, but then falls apart when you show it new data because it didn't learn the general principles.
Right.
Bishop's curve-fitting example, again, imagine using a super complex polynomial. It can whittle perfectly through every single training point.
But it looks crazy between the points.
Exactly. It oscillates wildly and doesn't capture the real trends at all. That's overfitting.
So how do you fight it? You mentioned the validation set.
Yeah, validation helps select models that aren't overly complex. Bishop also points to Bayesian methods, which kind of average over many models, making them less likely to overfit. And then there are regularization techniques.
Regularization.
Yeah, it's like adding a penalty term that discourages the model from becoming too complex, pushing it towards simpler, hopefully more generalizable solutions.
Okay, so overfitting is bad. Too complex. What's the flip side?
Underfitting. That's when the model is too simple. It's not flexible enough to capture the underlying patterns even in the training data. So it performs poorly on the training set, and it also performs poorly on new data.
So in the curve fitting, that would be like trying to fit a straight line to data that's clearly curved.
Exactly. A low-order polynomial just might not have the capacity to learn the relationship. It's like trying to build something complicated with only a hammer.
Right, so you've got this balancing act. Not too complex, not too simple.
That's the core challenge. Model selection, Bishop calls it. Finding that sweet spot. And that's where comparing models on the validation set is key. Or using techniques like cross-validation, which is a more robust way to estimate performance by repeatedly splitting and training.
Makes sense. Okay, we've talked about the data we feed in, splitting it up. But the raw data itself might not always be perfect for the model, right? Is that where feature engineering comes in?
Absolutely. Feature engineering is, well, it's often where the magic happens. It's kind of an art and a science.
Right.
It's about selecting, transforming, creating features, the input variables from your raw data to make it easier for the algorithm to learn. Better features often lead to much better models, even with simpler algorithms.
So preparing the ingredients, like you said, before cooking.
Exactly. Good preparation makes a difference.
What are some examples? How do you transform features?
Well, Bishop mentions using nonlinear basis functions. Even if you have a linear model, you can create new features that are nonlinear transformations of the original ones. Like, if you have an input x, you could create a new feature x squared.
Ah, so the model can learn curves even if it's technically linear.
Right. It gives the model more flexibility. Another common one is handling categorical data, things like red, green, blue. You often can't just feed those words in.
What do you do?
A standard technique Bishop hints at is one-hot encoding. You create a new binary feature for each category. So is red, is green, is blue. Each gets its own column with a 1 or 0.
Okay, that makes sense. It makes the categories understandable for the math.
Yeah. And Mitchell emphasizes how crucial representation is. The features you choose, how you represent the input, can dramatically affect performance. Think about neural networks. The input layer design is critical.
And sometimes you even create totally new features.
Definitely. Using domain knowledge, understanding the problem, you might combine existing features or calculate new ones that you think are more informative. Mitchell calls this constructive induction in rule learning, building better features.
Fascinating. So data prep is key. Okay, we've prepped data, split it, trained, tuned, tried to avoid over-underfitting. Now, how do we actually score the final model? How do we know if it's good? Evaluation metrics, I assume.
Exactly. You need quantitative ways to measure performance. and the right metric depends heavily on the task.
Okay, let's take classification first, predicting categories like spam or not spam. What do we look at?
The simplest is accuracy. What percentage did it get right?
Seems straightforward.
It is, but it can be misleading. Imagine a data set where 99% is not spam. A model that just predicts not spam all the time gets 99% accuracy, but it's useless for catching spam.
Ah, good point. So accuracy isn't always the whole story.
Definitely not. That's why we often look at loss functions, as Bishop discusses. They quantify the cost of different errors.
Cost, yeah.
Yeah. His cancer diagnosis example is powerful. Misclassifying a malignant tumor as benign, a false negative, is way, way worse than misclassifying a benign one as malignant, a false positive. The loss function reflects these different costs.
So you penalize the more dangerous errors more heavily.
Precisely. Mitchell also mentions cross-entropy, another common loss function, especially for probabilistic models. The choice really matters.
Okay, that makes sense for classification. What about regression, where you're predicting a number, like house price?
For regression, common metrics measure how close the predictions are to the actual values. Bishop mentions sum of squares error. You look at the difference between predicted and actual, square it, so negatives don't cancel positives, and sum them up. Lower is better.
So you're measuring the overall size of the errors.
Pretty much. There are variations like root mean squared error, or RMAC, or mean absolute error, MAE, but they all try to quantify prediction error.
So the big takeaway is you have to pick the metric that actually matches what you care about for the specific problem.
Absolutely. Minimizing false negatives in medical diagnosis, maximizing click-through rate in advertising, minimizing prediction error in finance. The goal dictates the metric.
This has been, wow, really clarifying. We've covered the main learning style, supervised, unsupervised reinforcement, the whole process of splitting data training, validation, testing.
And the pitfalls of overfitting and underfitting.
Right. And then feature engineering, making the data work better. And finally, how to actually measure success with the right evaluation metrics.
It really provides that core framework. Understanding these pieces helps make sense of almost any machine learning application you encounter.
Yeah, it feels like a really solid base. So for everyone listening, hopefully this gives you that foundation. If you want to go deeper, maybe pick one area, like look into specific supervised algorithms like logistic regression, or dive into k-means for unsupervised.
Or explore different feature engineering tricks, so look up metrics like F1 score or AUC for classification. There's always more to learn.
Definitely. And maybe a final thought to leave people with. As you start seeing machine learning everywhere, think about this. These models can be amazing at finding patterns, incredible really, but the real insight, the deeper understanding, often comes from figuring out why those patterns exist in the data in the first place.
That's a great point. Moving beyond the what to the why.
Exactly. What new questions does that ability to find patterns unlock for you? Something to think about. Thanks for joining us for this deep dive.